Hi, my name is Sadegh Rabiee. I'm a PhD student at the Autonomous Mobile Robotics Laboratory at the University of Texas at Austin. I'm glad to present to you our work titled IVSLAM, Introspective Vision for Simultaneous Localization and Mapping. It is work done together with Joydeep Biswas. In IVSLAM, the goal is to estimate the pose of the camera and make a 3D map of the environment given monocular, stereo, or RGBD images. This is achieved by finding correspondences across images. Existing solutions to IVSLAM assume that errors in feature extraction and matching are independent and identically distributed, but this assumption is known to not be true. Features extracted from low contrast regions of the image exhibit wider error distributions than features from sharp corners. Due to this assumption, IVSLAM algorithms are prone to catastrophic failures when sensed images include challenging conditions such as specular reflections, lens flare, or shadows of dynamic objects. To address this shortcoming, we introduce IVSLAM. IVSLAM builds a context-aware noise model that explicitly accounts for heteroscedastic noise and learns to account for bad correspondences, moving objects, non-rigid objects, and other causes of errors. During the online inference phase, images are passed through the introspection function, which predicts the reliability of image features as a function of locations on the image. The predicted reliability is then used to guide informative feature extraction by the IVSLAM frontend and to generate image feature-specific robust loss functions when solving for the pose of the camera in the backend. IVSLAM trains the introspection function, which is implemented as a fully convolutional neural network in an autonomously supervised manner. During runtime, for each captured image, features are extracted and matched with previous images and 3D map points. Then the pose of the camera at current frame is estimated given those correspondences. The estimated relative pose of the camera is compared with the reference camera poses obtained by a LiDAR-based SLAM solution. If there is a large difference between the two indicating an unreliable estimate of the camera pose by IVSLAM, this frame will be skipped and will not be used for generating training data. Otherwise, we proceed and evaluate the matched image features given the reprojection error of their corresponding 3D map points. Then a Gaussian process regressor is used to convert the set of sparse error values across the image to a continuous error heat map, along with the corresponding uncertainty estimate, which is thresholded to obtain a binary mask. The introspection function is trained using a mean squared error loss that is only applied to the unmasked regions of the image. Generating the training data in this autonomously supervised fashion removes the need for high-fidelity ground truth, such as the depth of the scene, for evaluating the image features. This makes IVSLAM a great fit for lifelong learning, where we would like a robot to continuously learn and improve its performance over time. As mentioned earlier, IVSLAM leverages the output of the introspection function when solving for the pose of the camera in the backend. In IVSLAM, the pose of the camera and the map of the environment are jointly optimized for such that it minimizes the reprojection error of the 3D map points onto the image planes. This is referred to as the bundle adjustment problem. What IVSLAM does differently here is generating a context-aware loss function specific to each image feature. It uses a Huber loss function with the parameter delta being provided for each image feature by the introspection function. A larger delta value leads to a steeper loss function and corresponds to a more reliable image feature. We implement IVSLAM on top of OrbSLAM, and by running experiments on extended real-world and simulated data, we demonstrate that IVSLAM significantly reduces the tracking error and increases the mean distance between tracking failures by more than 70% on challenging real robot data compared to the baseline. Here you see an example deployment session with the IVSLAM output shown on the left and the baseline OrbSLAM on the right. Here the baseline IVSLAM method picks up features on the shadow of the robot. However, IVSLAM rejects most of the bad features, actively inserts features from the good regions, and also accounts for predicted variance in the reprojection error of the remaining features. This leads to IVSLAM correctly tracking the motion of the robot while the baseline method wrongly estimates that the robot is stopped. With that, we come to the end of this presentation. Thank you very much for your attention. To find out more about IVSLAM, including the source code, please visit the project webpage. If you have any questions regarding this work, please feel free to contact me via email.